started. Hopefully everyone had a good fall break. Let's keep going with authentication. You all can talk about signing each other's keys and trying to verify each other's identities, and hopefully you're learning a lot about trust.
Non-existent.
Or distrust, maybe. Cool. Okay, so to refresh everyone, since it's been a week since we've met and talked about this, we are talking about authentication. So what are the aspects? What is an authentication system trying to do in the larger context of security? Yeah.
Making sure someone is who they say they are.
Yeah, trying to verify who somebody is, right? So trying to, whereas authorization says what you're allowed to do, authentication asks the question of who are you? So what are some of the ways that we can do authentication? Yeah. Username and password, and what is that actually authenticating? Why is that authenticating you? Yeah, so it should be the user that created the account is the only one that knows the password to that account. Great. What are some other types of authentication mechanisms which we talked about? Yeah.
Physical location.
Physical location, what else?
Using your phone to verify.
Using your phone or a secondary device in order to verify, so you're verifying that somebody has control of that device. What else?
Fingerprint scanners.
Yeah. Oh, sorry. Spencer, yeah, fingerprint scanners over here. Biometrics generally, so what's a biometric that's not a fingerprint? Iris, yeah, so like eye scanners, all this kind of stuff. Facial recognition. All right, so we talked about an authentication system as having, we can think of it abstractly as having different types of functions. And so we can think of an authentication system that is trying to map who the user is to their identity in the system. And so we have a number of functions here we can think about. We can have a set of authentication information, a set of complementary information, functions to turn an authentication information into complementary information, and a function that verifies somebody's identity and says, yes, they are who they say they are. And we looked at the UNIX system. So we looked at kind of classic UNIX authentication, has strings of 8 characters or less passwords, has complementary information where it's storing the hash along with a 2-character hash ID, which essentially acts, as we talked about, as our salt, and where now our function that translates somebody's password into the complementary information is a version of DES that's specific to the hash ID and has different ways to log in. So we looked at and we saw kind of the whole process of an external entity logging in and authenticating to a server using their password and how the server is actually able to verify their information. So why, here in this example, are we storing, why are we storing with Alice this thing that's not Alice's password? It's a hash of her password. Why are we storing that? What's the conceptual reason why? Yeah.
If the server database is leaked, you don't want everyone to see plain text passwords.
Yeah, so a hash is a one-way function, right? Meaning that it's easy to compute, given a password, compute the hash. It's difficult to go backwards, to go from the hash and find the password that maps to that exact value. Cool. So now if we put on our attacker's hat, what's our goal as an attacker? So how can we attack an authentication system? Yeah.
Find whatever the hash function is.
Find whatever the hash function is. How does that help us?
So we can use that to determine how they generate the hashes.
Okay, so so I guess that goes to threat modeling here. So what's our model, right? Does the attacker have knowledge of the system or not, right? We'll take a similar approach we took in crypto, where we assume the attacker knows the system, because otherwise then we're banking on the fact that they don't understand how the system works, right? That they're smart. We want the system to still be secure even if they know exactly how the system works. So that's a good point. What other goals do we have? Yeah.
So because if I remember correctly, hashing is about integrity of the message as opposed to It's like probabilistically impossible, but you want to find a way to do that, and that way they get the hash, and the actual message will be like very different from what they see.
Okay, so then let's go. So we're kind of talking more about how to break this specific hash function, right? One of the ways is find a different password that hashes to that same value. The system will think that that's the same password because that's all it does to verify. But at a high level, when we think of it in terms of this authentication system, what is the attacker trying to do? Or what would the attacker like to do? Or what are even the goals of the attacker? What's the attacker trying to do here? Yeah.
You want to convince the system that you're someone you're not?
Yeah, so we want to impersonate or spoof to the system and pretend that we're somebody we're not. Right? Yeah.
If you have a list of like repeating hashes and you can find whatever.
Forget hashes. I'm not thinking about hashes anymore, right? Let's think about high level. What's the goal? So, okay, we want to impersonate somebody. So how can we do that? What do we need to do that?
You need somebody to impersonate.
We need somebody to impersonate, so we maybe need to know about a user account or a user. Yeah, what else? Yeah.
We need to know what attributes that user uses to access any data that we're trying to grab on them.
Yeah, so what does that user use to authenticate to the system?
Username.
Their username and their authentication information, right? That's that A. Maybe it's their fingerprint. We don't actually care, right? This model doesn't actually specify what that authentication method is. But what if we steal that information? Right? Is that good? Can we impersonate the user at this point?
Potentially.
Potentially? Why? Why not?
There could be some other varying factors other than that.
But this is everything in our model, right? Our model says that the user inputs some authentication method A, and then, so something from our authentication set, there's a function that then maps that to the complementary information, and that complementary information is then matched with whatever's in the database. If it's in there, we're good, right? So at a high level, this is all we care about. Can we find an A such that for one of the, or the specific function that maps the authentication information to complementary information, that's correct for that user, right? So this is our goal. Okay, so we can think about different ways to do this. So, and this is what we've been talking about and focusing on, right? So if the attacker has complementary information, right? So like, this would be the case that the hashes of the server are leaked, right? Then the attacker's goal becomes find some A such that when you pass it through this function, the hash function, it gives you C. Yeah.
So if you're saying that finds like some A such that f of A equals some C in the C set, isn't
Yes.
the set C just the set of all possible like
Yeah.
stored rather than actually a valid password in the system?
Let's say that it's specifically, this is given for a certain user. And this, so this one attacker goal, this would be that C is associated with some entity. So yeah, you need another clause on there that says the login function returns true. So yes. So if the hashes and the passwords are the same, is this a difficult goal for the attacker or an easy goal for the attacker? So they've stolen complementary information from the server. Yeah.
I mean, I feel like this will be kind of hard because you have to brute force a bunch of plain text passwords.
But so let's say the complementary information is the same as the password,
Oh, okay.
right? So plain text, we can think of plain text passwords,
Yeah, easy.
right? Easy because this F is the identity function, right? Pass in something, do nothing to it, and return it. So the attacker can easily log in, right? But now with this, so if this F is a true cryptographic hash function, what does that mean if you have C? Yeah.
Pretty image resistance, so it's pretty much impossible to get A.
Yeah, so it should be, you should have to brute force all possible 2 to the whatever the strength of the hash function, 2 to the 256 possible passwords to find one that maps to the same value. What would you rather brute force instead? What would be another technique? So this would be breaking the hash function. Yeah.
Maybe just try a bunch of really, I mean, I guess if it's one user, I don't know, but like a dictionary attack with a bunch of common passwords.
Yeah, so what if I tried the password as a password? Right? Put that through the hash function, see if that's the value. What would you try after password?
Password 1.
Password 1? What else? What are other common passwords? Please don't say your actual password. And if you're using any of these passwords that we're talking about, you should change that. Which one?
1, 2, 3, 4, 5, 6.
Yeah, 1, 2, 3, 4, 5, 6. Yeah.
The birth date is for a loved one's name.
Birth date, or maybe somebody that they know, somebody in the family's name. Yeah.
Astif court.
What is that?
Astif court, ASDF.
Oh, yeah, ASDF, and then the first character is a QWERTY. Yeah.
Your name or your username.
Yeah, the user's name or their username. Yeah. Let's go back here.
Anything like vulnerable to like a dictionary text?
Yeah, we could try all words in the dictionary, right? That would be, we talked about that, there's probably 30,000 of them. I don't know the exact number, but that would be pretty easy to check with a good hash function. Cool, okay, so what if we don't have the complementary information? So this would be the case of, let's say you are, you're trying to break into, let's say some web service that has a username and password. So what are you trying to do in that sense? What's your goal? Yeah.
You just need any valid username and password.
So you need any valid username and password, right? So you're saying we define some password such that when I pass it through a login function, it returns true, right? So this login, so what's the key difference between these two approaches? Fundamentally, what's the actual difference here? I mean, some difference is clear, right? One, here we have a complementary information, here we don't.
Can you define the complementary information again?
The hash, we'll think of that as the hash right now. Right? So let's say there's a website. What's the difference between having access to the complementary information or not? So think about the situation with the website, yeah.
The second one is like complete brute forcing, but the first one is kind of like tracking.
Yeah, okay, so two separate things, right? So in one case, we still have to guess A's, so we can't really, in some sense, backtrack because we don't, if it's a good hash function, we can't go backwards, right?
Well,
So
you can't go backwards, but if you have like multiple hashes, the same thing, like you can determine what the rest of the hashes are.
okay, so yeah, you could, if you had multiple hashes, you could easily guess it in parallel in some sense. You could also, yeah.
I'm just saying, like, so for both of them, you're still guessing and checking, but one, you're guessing and checking against a non-true value. The other one, you have to hit the web server to authenticate every single time.
Yeah, so here you never have to talk to the website at all. You can just compute this locally, right, to try to break these. Whereas here you have to actually log in and try logging into the website. What happens, anybody have a smartphone? What happens when you mistype your PIN or passcode for 5 or 6 times in a row?
You get locked out.
You get locked out. Why does it do that?
So you can't just one person.
Yeah, to prevent you from easily brute forcing, right, the PIN code. You can get 5 or 6 guesses when they're all incorrect in a row. It locks your phone so you can't try for a minute. Where is that enforced in this model? The second one, right? It has to be this login function, right? Because otherwise, I mean, the phone is literally doing exactly this, right? Putting the passcode, checking it against something. If you had the hash that it was looking for, you could easily brute force and crack this. But you don't, and you're trying to brute force it without any of the complementary information. So you're trying to brute force pins. And because it knows you're using the login information, it can make that process slow and put up barriers in there so you can't easily guess through that. attacks. So we've looked at some things, we've just talked about some of them. Right, so we know what the attacker wants to do. Yeah.
Have nothing worth stealing.
Have nothing worth stealing. Yeah, that'd be a pretty boring existence, I guess. Or web service. I'd say even if you think you have nothing worth stealing, there probably is something worth stealing on there. Yeah.
Maybe having two-factor authentication.
So maybe using multiple of those factors, so maybe increasing the difficulty to an attacker. Does that fundamentally prevent them? Yeah. Not quite. Yeah.
Maybe lock an account after 5 failed attempts.
So we could, like we said, we could lock an account, and then what happens? How do they unlock their account? They're just completely hosed. They can never access your service ever again.
Email reset.
Probably just send an email to the people who run it.
Maybe so force them to send an email to reset their password to get access to their account. So, but now, so then the attacker would have to control their email. Another way to do it would be to force them to call customer support, reset, and unlock their account. Yeah.
Couldn't you just have them forced to wait like a day to try to move on, or an hour, depending on how many attempts there were?
Yeah, sure. You could force them to wait a day or an hour. Is that great for usability?
No.
Yeah. I mean, people frequently, I mean, I just did this the other day of almost locking up, I can't remember if it was an iPhone or an iPad, because I kept putting the password in wrong. And it locked up for 5 minutes, and I had to make sure my next one was good, otherwise it was going to be locked for like an hour or something, right? Which is very, very annoying. What else? So maybe, we talked about this a little bit, but maybe we can try to hide some information, right? Right? We can try to hide the authentication information. We can hide the function that we're using. We can hide the complementary information. So we talked about this on UNIX, right? So we talked about the UNIX, we looked at how passwords and hashes are done, but where are passwords actually stored on a UNIX system? When you SSH to general, well, I don't know that general is a great example, but when you SSH to like a standard Unix server, you type your username and password, where are the passwords stored?
Shadow file.
In the shadow file, so an etc shadow, right? So it's in a special file that's only readable by root. So you as a user can't access it. So we can try to, and again, this is the alternative being if your passwords are all available, your passwords A are just freely open to everyone, you basically made the attacker's life very easy. So we definitely don't want to give passwords away. We want to try to hide and prevent people from learning the complementary information. Can we hide the login function? Right, so we looked at the other way. So if we prevent people from getting the complementary information, then we can say at least they can't just try to brute force or guess things offline. Right, but we have this set of logging functions, or this login function. Can we just hide that and prevent the attacker from accessing it? What was that?
Obfuscate like at least how it operates on the two inputs.
You can obfuscate how it works, sure, but is that going to stop? I mean, what's that going to prevent the attacker from doing?
Just is figuring out how it processes the data.
But do they care how it processes the data?
I feel like if you get access to C, you can still limit which hash functions it is just by the size of C. Like if it's 256.
Yeah, so even trying to limit the hash functions, this is why we want to use the same cryptographic argument where we say assume that the adversary knows how the system works, right? The security through lack of, because, well, if they just get one piece of complementary information, maybe, but if you have an account on there so you know what your password is, you could try a bunch of hash functions until you find the correct one. What about the login functionality? Can we just hide that?
No.
Why not? Now somebody needs to log in, right? You need somebody to log in. So the way to think about this, it's like, I don't know, making a house where there's no doors on it, right? Going back to the house example, like sure, nobody can break into your house through your front door or windows or whatever, but now nobody else can access that house either. So similar to this, and this is the way to think about this, is that, but what information can we hide? So again, what information does an attacker know? Or what do they need to, so let's go back to the attacker goals. What does the attacker need to be successful when attacking an authentication system?
The user's credentials.
They need to know the password, so the user's credentials. What else? That's it? Yeah. At this point, if I know your password, I don't need to know the hash function, right? Because I don't care. It will take care of that for me. What do I need to know, though?
Username?
Your username, right? So, what information can the login service provide that makes the attacker's job easier? So, I mean, yeah, you guys have used websites before, right? Have you ever, what are some error messages you've got back when you tried to log in?
Well, I mean, it might, instead of telling you it's a bad combination, it might say the user doesn't exist.
Yeah, so, right, so you can say different information in a normal web service. It'll say something, well, not a normal, but rather than the login function just saying yes, you're logged in or false, you're not logged in, you can think of other information that sites give you, right? That the username doesn't exist. And why do they say that?
Just let you know that you didn't have a username.
Yeah, for user experience, right? So to make the actual user that's logging in, maybe they accidentally mistyped their email address or whatever the username is. They added a 1, they used a username from a different site, right? So then what else, so if it's giving you that information, then what other information is it giving you?
Who doesn't exist?
Yeah, so it tells you who doesn't exist, and then if you type in a real user ID but the wrong password, then what does it tell you?
It's a valid username.
Yeah, it'll say, so if it tells you if the user doesn't exist, the user does not exist. But if the user does exist and the password is wrong, it tells you the password is wrong. You can use this information to figure out what user accounts exist on the system. What are some popular online services that you use where you don't have to guess what people's usernames are? Twitter? Yeah, why Twitter? Yeah, it's built into the service, right? You can go look up every one single person's user ID, and you can use that user ID to log in. What else?
Instagram too.
Instagram? What else? Was it?
Social media.
Yeah, most social media. What? So if it's usually not your username, then what do you use to log in? What's your user, like what is that username? Email? Are your emails private? Your email accounts? Especially if you're using your ASU email, as you're well aware, you can search that, look up that stuff if you're a student. What about if you're not a student? Do you need to worry about that? Yes, why?
Probably use that email somewhere.
Yeah, where would you have used that email that maybe it's public? Piazza is not public, thankfully, but maybe. I mean, maybe if Piazza post becomes public. Yeah.
If you sign up for a newsletter, then people know they might be distributing your email.
Yeah, so you maybe sign up for a newsletter, you don't know where that email propagates from there. What else?
GitHub,
GitHub, so your GitHub,
you can make commits.
you can make it, oh yeah, that's right. When you make a commit on GitHub, your email address is usually in that commit. What else?
Your LinkedIn account.
LinkedIn usually has your email address. What else? Yeah.
We've been giving out our emails the last few days.
Yeah, oh, I mean on Piazza, right? But publicly, you if you have a website where you have a contact information, that'll have your email address on it. If you've ever made any post to a public mailing list, those are usually archived and publicly available, so those email addresses are there, right? So, anyways. So, we can't hide L completely. This is kind of the idea here. So you need to actually be able to log in. But what we can do is we can try to, one of the good techniques is to not reveal as much information as possible about if the attack succeeds or not, right? So, but again, it's a user experience trade-off. So this is kind of a business decision that different services need to take into consideration if they should give you information about the username not existing, or because if I know the user IDs are email addresses, right, I could actually just get and harvest a bunch of email addresses and start trying to log in as them, and I'll know which which email addresses exist or not. What are there web services that exist where even the fact that you're a user of that service would be sensitive information?
Yes.
Yeah? Maybe one of them suggest an example that's appropriate for the class.
What's the name of that one website where people would go have affairs?
Adult Friend Finder, I believe. Or actually that's, yeah. Yeah, right? Yeah, so we won't get to it, but they actually had a big data breach. So they had usernames, email addresses, and I think hashes of passwords got leaked. And then people actually used that information to then go extort members of the site. So they would figure out from their email address, maybe their LinkedIn, who they were, if they were married, and then send them emails saying, pay me money, or else I'm going to tell your family that you were on this site. So real world impact, right, of just even knowing that somebody has an account on this site. Yeah.
Doesn't hiding out put pressure on the consumer to use a different username and passwords for every site they use? So, like, how many? I know I use the same username for multiple things. It might be less secure, but I am lazy. So, again,
It's a choice, right? So I think the key is one of the good principle is to not leak information to the attacker about what accounts are valid or not. For instance, if you knew there was an admin user on the account, that would give you a high value target to try to break their specific password. Whereas maybe for other sites it doesn't matter, right? So, and I think obfuscating as we'll see, you should choose a password such that it doesn't matter that somebody knows your user ID, right? So that's more on the user. So it's not necessarily about obfuscating your user ID and using a separate user ID per service. It's more about an attacker easily. So if I was, let's say, if I was going to try to break into a company's maybe not internal web portal, but some web portal for their company, I would try different emails. So I'd harvest all the emails at that company, and I'd try those emails. Oh, actually, GitHub's a great example, right? So I'd try to harvest all those emails from that company. I would try logging into GitHub to shrink that list down to user ID, to email addresses that I know exist on GitHub and are associated with this company. And then that would give me a list of users to brute force from there. Cool. So there's other things we can do. We can prevent access to L in some sense, right? So we could do something like, so for instance, my ASU, right? So there's a clear username password login that you all have, right, to access my ASU. Can anyone try to guess your username password on your my ASU? Yeah, right? Anyone from anywhere. But you can see ASU restricting access to only if you're inside the ASU network. Why would they want to do that?
So people externally can't just like spray it.
Yeah, so this way people externally can't just randomly guess username passwords and maybe guess it because the password is password. Right? Well, what's the downside there? Yeah, it would be pretty annoying to have to like sign up for classes or access, not Blackboard anymore, what is it? Something else? Canvas. Yeah, access that stuff from not always at ASU. If you were traveling or whatever, you'd just be completely on your own with access there. So this happens a lot in terms of a company or corporation could do things like only allow access to some certain system from specific IP addresses, either internal to the company or whitelisted from people's homes or something like that. So this is yeah.
So how do you whitelist like an IP address? Don't they change? Like if then you connect to a new network?
What IP address are you talking about specifically?
So like I guess as an example for that company,
Yeah.
like your one at home, if you reset your modem or router.
Yes, and you would have not access to your whatever system, and you'd have to tell somebody to whitelist a new IP address. Yeah, so IP address, this is why this is not a great idea. It's not very user-friendly at all, but you're restricting the space of people who can try active password guessing attacks against your service. Okay, so password-based authentication. So this is the one we've been focusing on the most. In your computing, using computers, managing username, passwords accounts, would you agree that this is the most common form of authentication that you come across? Yeah, what do you think about it? As somebody who's used this for, I don't know, I guess how old you are, X number of years. Yeah.
It's got a lot of flaws in it, but it's one of the most, since it's like the most widely used thing, it's also the most easiest for people to have, like change the system would be more complicated, because you're just so used to having a password phrase.
Right, so let's break it down, I mean, a little bit more, right? So you said there's flaws, but what are the flaws? Yeah.
Oh, I was going to list positive. It's easy to implement.
It's, say it again?
It's easy to implement.
Ooh, it's easy to implement. Is that a good thing or a bad thing? Yeah, interesting. We'll look at some of the implications there. So, okay, easy to implement, a pro. Yeah.
For all the research stuff for how to protect your passwords, there's equally amount of research stuff on how to break your passwords.
Yeah, so there's a lot of, I mean, this is, I'd say, no matter, in some sense, you have this problem that Windows had back in the day where when it had the 90% market share, all of the malicious software was written and targeted towards Windows. So people who ran Mac software and Apple software thought that their system was safe and secure. And it was really just because an attacker is not going to put the effort in to target your specific system. So it wasn't until like Macs got more popular that there started to be like Mac viruses and those type of malicious software. So yeah, it's an interesting thing. It's in some sense because it's so dominant, it gets attacked and defended a lot. But that definitely is something to worry about. Let's go someone else. Pros, cons? Yeah.
I think the passwords are a hassle.
Passwords are a hassle. Why?
Because everybody wants a different one. There's so many. You forget them.
How many passwords do you have personally? Would you be able to share?
I have like 3 or 4 passwords that I use, and I do little iterations on each of them, like adding things or whatever.
Yeah, you don't have to tell us your specific algorithm. It's okay. But okay, so yeah, so what? Okay, yeah. Right.
It could be convenient for certain users that want to share their accounts.
Yeah, so a pro would be convenient to share accounts. Does anybody actually do that? Yeah, it's clear that that can happen very easily with an online service where it's not necessarily tied to you, especially if that service lets you create different profiles to use. Yeah.
I was gonna say the con is that most of the time it's human generated, so sometimes humans can be predictable or just make weak decisions.
Right, so a con in terms of password strength, right? Because so let's say an adversary wants to, well, we talked about this, right? They want to break into maybe your account specifically, right? They could just try all the common passwords. They can try if your password is just a single word that's easily guessable in a dictionary. Maybe depending on, there's lists, we'll talk about them in a second, of like frequently used passwords. And so you can go in order of most frequent to least frequently used passwords and just guess those. So it's up to the user. So from a usability perspective, this puts a lot of burden on the users to generate a password that's difficult to guess, but that is unique and different for every site. How many websites do you have passwords for? Yeah.
Over 100.
Over 100? Anybody think they have significantly less than that? Yeah?
I'd say like
30?
30.
Do you think you have 30 web accounts only? I don't know. I think if any number is believable, I probably wouldn't believe 2. Just like your MySU account, your CSE submission server. Only 2 you ever need. It is the only thing that matters, I agree. So what other things with passwords? Okay, so so does anybody actually have 100 different unique passwords that they've memorized that are difficult to guess for all their websites? Memorized.
Password manager.
Yeah, okay, so we'll get there in a second, but, right, so that seems insane. What's the problem with reusing passwords based on kind of what we've seen and what we talked about? So why do we give advice that you should have a different password for all these accounts? Yeah.
Like if somebody figures out you're using your password authentication, they can try other websites and use the same
passwords, especially with an associated account, means that if I ever guess your password for one site, now I've leveraged that to 100 different websites, right? And think about, so if you have, say, passwords, accounts across the broad internet of 100, on 100 different sites, do they all have good levels of security? I mean, probably not, right? I mean, yeah, exactly, shrug, like some of them, hopefully, but even big companies get breached. The worst probably the worst part about a small website is not only is it likely to get breached, but nobody's ever likely to notice or tell you about it. Right? And if you're using the same password on all of them, now your attack surface on the internet is huge. All I need to do is break into one site that I know has an account for you, and then steal that password. Now I can log into any website. Or what's, again, I think we've talked about this before, but what's the ultimate, if you could only steal one of my accounts, what would you want to steal, or websites? Your email. Why email? Reset password, right? The reset password functionality, all the password reset links get sent to your email, which you click on to create a new password on that website, right? So just by leveraging access to my email, you could then get access to probably 85 to 90% of those other websites. The only ones that would probably, I think the financial services don't let you change a password like that. You probably have to call and talk to somebody. But what kind of things are they going to ask you when you call to change your password? So how does it, or sorry, another way to phrase that is, do you give your username and password when you call a customer service representative of your bank? No, when you get it. Social Security, what else? Account number, maybe address, PIN number, maybe a PIN number. Place of work, yeah, they could try to verify what information they have. If you have access to somebody's email, what information do you have? Does anybody have their social security number in their email? No? Not in the email address. In your archive, your email archive. Yeah, somewhere, have you ever sent or received an email that has your social security number on? Or the last 4 digits of your social?
Yes.
Yeah, anybody ever, I mean, you, oftentimes for a company, when you get a job at a company, you need to give them your social security number. That sometimes happens over email. Other things, taxes or any type of that. If you have any tax returns, your social security number is on your tax returns. If you've ever stored that or sent it to yourself or done something like that in an email, it could be in there. It could be reimbursement for something. You went on a trip for some club and then you had to send somebody a form with your social security number in order to get reimbursed. Yeah.
Well, you can also get access to some other site that might have storage.
Yeah, so then there may be, in those other 95 websites, there may be something else where you've stored that, maybe in your Google Drive or in somewhere else, right? Similar things with, and I'm also thinking of things like, you may think, well, your driver's license number or your passport number, right? But for similar reasons, you actually may have sent scans of those documents to somebody else over email, and so that copy is now stored forever in your email. I'm also speaking from experience. I'm not trying to project. I know instances of all of these things that I haven't. I try not to do it, but sometimes you're just going to get stuff done, and so there exists in my emails copies of all of this information.
I think what's even worse on that side is like you send that doc to the other person. Well, how secure is their methods?
Yeah, exactly, right? And that's just the emails that you send that your site has received. And I think we'll get to network security and we'll see that it's also possible that other people saw that information along the way. But there's only so much stuff you can worry about at any one point. Okay, so passwords are the most common. Any other pros and cons or strengths and flaws that we didn't bring up and talk about? Yeah.
I don't like how 100% of its worth is laid on the password being confidential. It's pretty easy to trick people to give you their password.
Yeah, it's pretty easier to trick anybody. Well, no. So it's easy to trick. How would you trick people to give you your password? Just go up and ask them?
Fake email, like a fake login page.
Yeah, so fake email that says your a fake email that says your Google account, there's a security warning, somebody's trying to break into your Google account. You know, click here to either change your password, and then you click through, that takes you to a website that looks exactly like Google's login information. And then you type in your username and password, they go, great, all right, you're all good. Yeah.
Is there scam calls?
Scam calls, so people calling you trying to scam, robocalls. Yeah, the reason why these things happen is because they work, right? So in 2016, I don't have all the information here, but anyways, there's a number of these email phishing attacks that are high valued and actually work and compromise people. So people fall victim to this kind of thing all the time. So all you need at that point, most of the time, is their password, right? Once you solve their password, you're good and you can log in as them. Cool. Okay, so that's definitely a con. What else? Yeah.
Pro would be like, you don't have to do extra things. You can just have that piece of knowledge, and that's it. You don't have to have like a phone or a key or anything. You just
Okay, so the pro is you know that password. As long as you know that password, you can go to any machine anywhere, type in your username and password, log on to that service. Is that also a con? Yeah.
Yeah, it's a con because, like you said before, you can have software that reads keyboard input and know exactly what their password is.
Yeah, like this machine right here, right? This Dell machine in front, I have no idea what's running on this system. If I were to log in here with my email, username, and password, bang, that's stolen by somebody, and now they could get access to that, right? So it's a double-edged sword in some sense. And the flip side, and we've talked about this before, is forgetting your password, right? So if you forget your password, then you're the only one technically that knew that password. So there must be some way to try to reset your password. If not, then you're just completely locked out of your account for all eternity, right? Okay, so I think paraphrasing from Winston Churchill, passwords are the worst form of authentication except for all those other forms that have been tried from time to time. The original quote was about democracy. So, what are some other options? So maybe you've used or seen other options. What are some alternatives? Yeah.
Like we're talking about the mutable characteristics of your body being the authenticators. So
Yeah, so like on mobile, on cell phones, right, smartphones have ways to do other types, fingerprints, face recognitions, yeah.
if we don't really want to move away too much from passwords, we use like password managers, which can generate or store passwords.
Yeah, that's not really changing the system though, right? It's like how the user manages this insane system changes in some sense. What about, yeah,
Like those login tokens.
login tokens, what does that mean?
Like, you know, the things that change every 15, like a 6-digit token that changes every 15 seconds.
Yeah, but does it, can you just log in with that?
I feel like sometimes, right?
Maybe, I don't know.
But you still need a username and password and then the token.
Right, so you need a username and password and then something, so it has all the worst properties, most of the worst properties of passwords, and then making it even more difficult to use. Yeah.
We talked about the microchip that is provided for you. That way it can't be stolen.
Interesting. Okay, yeah, that's actually good, like building physical security authentication, right? You have some card that you can use to authenticate. What about to websites? Somebody mentioned Instagram. Well, maybe does everyone have, well, okay, that's not a good example. What about anyone use like login as Facebook or something? Login with a Facebook account? Never used anything like that? Login with Google or with your Google account. So what is that doing?
Put under trust on Google's security of your password.
Yeah, so it's interesting, right? It doesn't get rid of passwords entirely, but it allows one site, instead of now creating 101 usernames and passwords that you now need to remember and remember the password of. Instead of that, they essentially trust Facebook or Google or whoever to authenticate you, and then they trust them when they say, hey, this is user XYZ. And maybe you can give them access to certain information or not, but at least then you don't have to create a new username and password for that service. Yeah.
So what do companies like Google and Facebook gain opening their API to allowing people to use that, like use the login as?
Ooh, what do you guys think? So what is Facebook, why does Facebook use this or create this feature? Yeah, back there. Say it louder. Yeah, so to acquire users, right? So you're having thousands upon thousands of websites like advertising for you, right? And have your brand there with a link to log in with Facebook. Yeah.
Data.
What was it?
Data.
Data, what data? How do they get the data?
Like personal user data, or, because sometimes when you log into a system like that, it'll be like, I want to know what you're doing with this service, and you have to like, you say yes.
Yeah, so Facebook is getting information from the service about what they're doing. Also, just even having that button, that login with Facebook button, is usually hosted by Facebook servers. So when anyone visits that site, it means they make a request to Facebook servers, which tells them the IP address of the person that's accessing it, any cookies that Facebook's seen about that user in the past. So it actually allows Facebook to track your behavior beyond what Facebook, right? When you're browsing just Facebook. Yeah.
They can also just run scripts to that button on the page.
They could. I don't think they do, but
Collecting more information.
we'll go with data collection. That's in the broad umbrella of data collection, right? Yeah.
Is there more reason to keep your Facebook account active? It's tied to other accounts too.
Yeah. What if you? How do you delete your Facebook account if you're tied into thousands of websites? Any other? Not to be an anti-Facebook rant, but yeah.
I was gonna say, like, on that topic of how do you disconnect that? I mean, most, like, in those, I think certain services, if you log in with like Google or Facebook, it's more of they're kind of authenticating you, but then they're pulling the information from that and they give you the option to make an account with them, so with that pulled information.
Yeah. So it's interesting. It's user friendly in some sense, right? You don't need to create a new username and password. That website may actually pull in information from you that you would have had to give to it to start a new account or whatever. And then they may try to force you to create a username and password so that you can still log in even if Facebook goes away, right? So yeah, all interesting and other types of authentication, but still you still have this problem of you still need a password to authenticate to Facebook or Google, right? Okay, so we talked about a little bit of passwords. So why are passwords easy to guess?
People like them simple.
People want what?
People want simple passwords.
People create simple passwords?
Yeah.
Why?
Because most people aren't computer science students who have numbers memorized constantly. They just want simple offhand.
Okay. Yeah. So maybe another way to phrase it is people maybe aren't aware of the risks of using an easy to guess password, so they use what's easy to remember. Yeah, back.
So what I was saying, in my mindset, I want to do an easy to guess password so I don't have to write it down so that someone else can take it, because then it's easy to guess, all I have to do is keep it in mind.
Yeah, so the tricky thing is easy to guess and easy to remember are two different things, right? It's possible to create a password that's hard to guess but easy to remember. It's possible, but for an average user, it's kind of a pain, right? Like you generating just, let's say, for like a UNIX password, 8 characters, you can generate a very secure password if it's random 8 digits, right? Because they're not digits, but alphanumeric, uppercase, lowercase, and numbers, because then you're getting 8 to whatever that to the 8. Anyways, you can increase the space of things to guess by randomly generating a password, but now you have to have this random piece of information that you memorize per website, right? Yeah. So there's this kind of inherent dichotomy, because you want a password that's difficult for other people to guess, but easy for you to remember. And this again goes back to, let's say you even created a random password that was 20 characters. You're going to create that for all the 100 different sites, or are you just going to reuse that same one across all of them? Right? Cool. Also easy to snoop. So how do you snoop on somebody's password?
Look over their shoulder.
Look over their shoulder. This is called the shoulder surfing attack. Right? So you just watch them as they type in their password. Did I tell you the story about this? So I worked for the Sacramento Sports Commission. Should I record this? That's fine. And we put on the Olympic trials in Sacramento, and so my job was to kind of help make badges for everyone. So you have badges with people's face and what areas they could access. So it was a whole access control system based on that. The software that we were using, we could predefine different access. So if you're an athlete, you get certain access to certain things. If you're a volunteer, you get access to certain things, which are obviously much less than an athlete. But if you're a volunteer who needs to work like with the athletes or in a certain area, you need to alter what areas they could access. So the software that we were using to do and create these badges, you had to put in a password if you wanted to change the default authentication, which is fine. That sounds great. The problem is we had volunteers creating these badges. So you have people you don't trust creating these badges for other volunteers. So, and this password field was not hidden. So what does that mean? So when you type in a password, it would show up exactly in plain text of exactly what you typed in, and then you could change things and then hit it. So you'd have to, like, if there's a volunteer right here, you have to tell them to literally you would have to tell them to turn away as you typed in the password and make sure nobody looked at it. So, okay, somebody said, well, that's crazy. There's no way we could do that. So what would be a secure alternative? Secure.
The black circles when you type it in.
Yeah, so somebody decided our password would be 5 asterisks. So as you type, and then you have to fake typing in other letters. Because otherwise it's very clear somebody's shoulder surfing. Or this actually happened to me one time, mistyping it. So they see asterisk, asterisk, AB, asterisk. So they can see that it's not hiding your password at all. Just to get around this terrible password. So snooping, all this kind of stuff is crazy. It's also, as we've talked about, easy to lose or forget. So no control on sharing. It's easy to social engineer, right? And these are kind of things that are inherent to passwords themselves, right? You have this ability here. Then there's a lot of practical vulnerabilities that they're susceptible, so kind of easy to snoop by other people as you're typing it in. It's also your password can be easily visible depending on the technology. So we talked a little bit on crypto about HTTPS secures and encrypts your communication with a web server. So if you're using a website that's not using HTTPS and you are typing in your password on an unsecured wireless network, like at a coffee shop, everyone with a radio can sniff your traffic and see exactly what your password is that you're sending to that site. So even if you're typing in a great password, they can still do that, yeah.
Don't most companies use like services now? So like those typically have mandatory some sort of standardized protocol, and sometimes they use HTTPS.
They should, I would say, yeah. Not every company does. It's getting better and better, and more companies and more and more websites are. The problem is, well, there's other ways where it's easy to do the wrong thing. Sometimes you can mess up your email client, and Google's good about this, but let's say your random company's web server, you can easily set it up to do authentication to your email server, sorry, not web server, your email server over plain text, essentially. There's tools you can download that will sniff wireless traffic. There was a tool, Facebook actually used to not only have HTTPS on its login page. So when you logged in and transmitted your password, it was secure, but then every other page after that was HTTP. The problem is, in order for Facebook to identify you and link your sessions, you needed a cookie value, right, that specified who you were, and that was sent over plain text. There was a tool that somebody developed called Firesheet that would listen to a Wi-Fi network and would show you all of the cookies that it stole and who those accounts were, and allow you to just pop up a new Firefox window with that specific user account. And Facebook fixed this in like 3 days. They HTTPS'd all their websites. And it was a big problem on college campuses because most of them were unsecured wireless networks, and so it kind of had a bad combination. Susceptible to replay attacks, as we talked about. This was kind of when we went last week over this idea of, do we hash a password before we send it to the server, right? Well, as long as somebody gets our hash, in that case, then they can replay it to the server and get access. Similar things here. Password reuse, and really kind of requires proactive management on the part of the user, right? We're forcing a lot of security decisions onto the users. Cool. And we'll kind of look into this. So one of the ways we've talked about, so a way of attacking the authentication of a service is just a dictionary attack. And we can attack essentially every single password-based authentication with this. We just try either different values in the dictionary. Somebody mentioned pet names. We could get the list of the most common pet names in the United States and try that, right? And if we have so this, again, it kind of depends on, you can think of different scenarios. Just trying on the website, we can try this. We can also, if we have the complementary information, we're trying to brute force a hash or check a hash. In this case, essentially, rather than brute forcing, we're just randomly trying all characters and all inputs. We're now trying specific values, like a targeted attack. So is it possible to search all possible passwords like this?
Using a dictionary? No.
Right? Why?
Most passwords are dictionary words.
Right, a password may not be, so the space, so think of it in terms of like sets, right? The set of all possible passwords is very, very large, right? So that's dependent on the specific service. We saw on UNIX that passwords were 8 characters. Were there any other restrictions? No, you can technically have a password that had null characters and crazy stuff that you could never actually type into it. You have to figure out how to get those in. But you theoretically could do it, right? What's a more likely password space? Yeah.
Well, most passwords these days require you to include like a dash or numeric values or at least some form of special character.
Yeah, so depending on the service, right, it may require a dash or a special character or uppercase character instead of just having lowercase characters. So if you only have lowercase characters, what's your set of, I don't know. So you have 26, right? 26 possible characters to guess for each element. Now what if you have uppercase? So you just doubled it and then add on 0 through 9. You've added 10 more possibilities. Then add in spaces, special characters, right? You've actually significantly increased the search. Well, not necessarily significantly, but you've definitely increased the search space, right? So maybe it's difficult to search for all possible passwords, but it's much easier to search for likely passwords, right? Again, this is where we're using the fact that these are humans writing these passwords to do this. And we can perform a dictionary attack, as we mentioned again, offline, so we know the function that's being used, and we have the hash, we have the complementary information, C. We can repeatedly try different guesses. There are super cool open source tools that you can use for this, like Crack or John the Ripper, that you can use to break these hashes and to brute force these hashes. They require some tweaking. You have to tell them what space of password you're trying to guess. So you're going to guess 3-character passwords that are just lowercase and uppercase, right? That could be one thing. So then this would be an offline attack. An online attack is when you're actually trying it against the service, right? And this is what we talked about with logging into a website. So, let's say a website is real secure and if you put in the incorrect password, let's say 3 times in a row, an incorrect password, it completely locks your account. Can you perform a dictionary attack against this website?
Not effectively.
You can just keep switching accounts.
Yeah, so no in some sense of if you're trying to break into one user's account. No, you can only try 2 passwords, or 3 passwords technically, and then the password is locked. But what can you do?
You just keep switching accounts and hope that, you know, someone uses one of those passwords and get it.
Yeah, so especially if this website gives me information on whether a user account exists or not, I can enumerate all user accounts, and then I'll try the most popular password that matches their security requirements on every single account. That'll likely get me 5–10% accounts, and then I still have a chance to try the second password, most common password on all the accounts. Yeah.
Not assuming they're doing everything correctly, because I know a lot of the times companies will put like the amount of time you can try the password in your cookies, and you can go in and change it back to 0 or whatever.
Assuming they do it correctly, yes. So actually even the iPhone, I never got to play with it, but I bought one of these forensic boxes that would brute force iPhone pins. And the way it would work is, because the counter for how many times you tried or the lock was stored essentially in memory and wasn't persistent. So you could just try, I think, 20 passwords and then kill the power of the phone and reboot it. And so like you think of like a 4-digit passcode that's just 0 through 9. It's actually, it only takes like 2 days for a device, a hardware device, to crack these kinds of things. Since then, the iPhone's got a lot better. They have a secure enclave now that you physically, even if you ripped apart the chip, you couldn't get into, and that's data is persisted there. So they had to step up their game a lot. But yeah, if you can get around technical requirements, then absolutely. So for instance, the other thing that websites do is they restrict how many times you can try based on IP address. So in that case, the attackers, rather than just trying from one machine over and over, they either use AWS or the criminals, so they use a botnet of machines that they got access to that are real people's machines, and they'll just try guesses from each of those machines. So it never goes above some threshold for detection.
What were we talking about?
Logging in.
Yeah, so you can guess the easy password across everyone's account. Yeah.
Couldn't whatever companies you're trying to log into could see these multiple login attempts and be like, someone's trying to break into our network and notify people or just be on alert.
How many notifications are you willing to get?
That's true.
Right? Anybody run us? I don't think we have time, but I can maybe show you my server logs of people trying to log into the SSH in our submission server. I'm sure maybe some of them is you trying to do that, but you can see there's just constant background noise of people guessing passwords. So the answer is yes, there's a ton of work in trying to detect that, but separating out the noise, normally what happens is they're not going to tell you, they're going to alert a security person that looks into it, and then if you need to change your password, they'll contact you. So how do we counter password guessing? I want to try to design a system that prevents this. Yeah.
Logging to a node, for example, like Google will say like, yeah, you're signing in from a computer, I don't recognize this.
Yeah, so we could maybe keep track of other information that the user is using when they log in. So again, we could try IP address. We could restrict it based on that. We could assume that the bad guys are very smart. Or again, if they've stolen our hash, then they don't need any of that at all, right? They can do it completely offline. So one way we could do that is just don't let them access the complementary information. Therefore, you can force all guesses to be online. The problem is this is very hard to guarantee, right? What else? Anybody mistype their password logging into their machine? What happens? It tells you to try again, and then if you got it wrong again, try again. Does it? How long does it take in between guesses? longer and longer? Is that because the hash gets more and more difficult to compute? No, the hash function is usually very quick. I mean, if you're using SHA-256 or MD5, the hash function is very quick. This is the login function intentionally adding an exponentially longer and longer delay so that somebody who's trying to break into your system and trying to guess your password will be delayed by doing that, right? So this is some of the things that we talked about. Let's add a delay to the login function when the password's incorrect, which should inconvenience real users very little, but makes dictionary attacks take longer, let's say. It doesn't fundamentally prevent them, but makes them take longer, yeah.
Like, I mean, that's a way of it. I know that I've done a system one, like, when I was a kid. I made it so that their iPod took like 10 minutes to unlock, right? So that's like kind of a denial of service.
Yep.
You can do that.
Yes, I mean that's definitely something. I mean, I have a terrible story where a friend did that to somebody else to try to mess with them, and then didn't realize the corporate policy on the iPhone meant that the third attempt would wipe the device. So yeah, the device just started wiping, and they were like, "Oh God, I made a huge mistake." But so the company made that decision, right? To say like, rather than let somebody brute force and get access to this device, we'll rather wipe it. For a common brute forcer, if you can slow them down on the order of minutes, so you probably have a cap, right? Potentially, depending on how you do this. But the key problem here is, we said it's probably easy, I mean, we can't force and guarantee our hashes or our complementary information to be secure. They may be released. And when they're released, then this delay we've added to L doesn't matter at all because they can do whatever they want. So what can we do to get around that? Yeah.
In the case of like offline dictionary attacks, there's like hashing algorithms that are intentionally designed to be slow, like decrypt, I think it's called, so it's just hard to iterate through all the possible passwords.
Yeah, so that's exactly. So what if we just increase the time to compute the hash function, right? We could use a different hash function that's designed for this. We could just SHA-256 10,000 times or 1,000,000 times. Just keep feeding the output into itself, right? That would do something similar. And now if somebody steals our passwords, if each guess takes them 30 seconds, then it's much more difficult to brute force. But if each guess takes them 30 seconds, how long is it going to take them to log in? At least 30 seconds, because we need to take their password and compute that hash, right? So usually these algorithms have a way to tune it, so it's on the order of 300 to 500 milliseconds, somewhere around there, where you're not going to know, but MD5, SHA-256 can be implemented insanely fast in hardware. They have systems to do that. One way, and we're not going to go into the details here, but rainbow tables are insanely cool, so if you're interested in this password cracking stuff, I suggest you look this up. The essential idea is, well, I know what standard passwords are, and I know what standard hash functions are used for logging in, so why not just pre-compute it, right? So what do I need to store in that case? What was it? Yeah, the password that I'm guessing and the hash. And then I go through a leaked data set, and I take each password and I compare it to the password hashes I already have. And if I found it, I know the password, right? So this is essentially what rainbow tables do. Pre-compute some size of the storage space. We're not going to go into the details of how they work, but essentially allows you a trade-off in time it takes to crack and the space required. So the space requirements are very large. So for instance, you can get download, and these are actually probably one of the best instances of torrents. You can get a rainbow table for MD5 that has all 1 through 8 character alphanumeric values in 127 gigabytes. You can now, but if you want to extend that to all 1 through 9 character alphanumeric characters, it's 690 gigabytes, right? So super cool technique, attacking technique. And again, space requirements, so you pre-computed this. But what if the authentication system is using a salt to the hash? Right? So the salt, as we talked about, is a random value that's unique per user. That information combined with the password gets you the hash. Right? So that doesn't help me here, because these are just all 1 through 8 character alphanumeric values that I have an MD5 for. It does not take any salt into account. So that way each password hash is unique, so that even if we have the same passwords, because we have different salts, the hashes become different. And essentially we think of it as selecting a different F, right? That function for every user. And just as we saw, with rainbow tables allow us to break. So now you need to generate a different rainbow table for every possible salt value, which just gets insane. The other way we can go about solving this problem is slow hashes. So this is a hash that has the cryptographic properties that we want. We never want to give those up, right? If it's easily reversible, we don't want that. So things like decrypt is designed to be a slow hash. It's actually used on the submission server, so I could give you my password for the submission server, and each hash takes about 300 milliseconds on average to compute, so you'll definitely not be able to break my password. And that also means I can't break your passwords. And so for those of you that have asked to get access to your password on the submission server, this is why I do not have it. I can't give you your password. I can change this so that you now have a different password that I create. Other functions that are interesting, so there's a whole kind of vein of research into slow hashes. Script is one that is designed to take up memory. So all of these things, a lot of these hash functions take very little memory, so they can be easily implemented in hardware, even on like an FPGA. But Script is designed to take maybe like 100 megabytes in order to, I don't know what the exact numbers are, but 100 megabytes in order to do it, which is difficult to make memory that is very fast. Okay, we talked about this. Cool. So we're going to go over an example of password reuse. So again, this is what we talked about. 3.5 billion Yahoo accounts, usernames, and hashes were released in 2013. There was 500,000 adult friend finder accounts released in 2016. This list I haven't updated, but there are always constantly breaches. The Adobe breach was super interesting because they had user IDs, they had email addresses, they had password data that was base64 encoded, and then they had the password hint. So the password hint, of course, needs to be shown to users, so it can't be hashed. It needs to be stored essentially in plain text. So you see that password hint in the corner says try QWERTY123. What do you think that user's password is? And so people looked at this and actually tried to figure out what this password data was, because it wasn't clearly a hash, because the password data got longer and longer, right? It wasn't all a fixed size. We know it's a hash if it was all fixed size. So here, you can see kind of by using the password hint, they were able to reverse engineer what the algorithm was. They were able to look at the different password lengths, able to figure out that essentially they were not hashing the passwords, they were encrypting the passwords. So this was passwords encrypt with either AES or DES or something like that. And what they found was, by reverse engineering this, they found these were the top passwords. Oh, sorry. They used a different account, that's right. They used these top passwords that were linked in other data sets to map them here. To find out that, yep, all of these were the password 1, 2, 3, 4, 5, 6. Not a great password. 1, 2, 3, 4, 5, 6, 7, 8. I think that's like twice as better. QWERTY 11111.